Okay. So let us start the session. Do you see my screen or not yet?
Not yet.
Okay. And now?
Still, we still don't see it,
Let
doctor.
us wait some time. Tell me when you see the document.
I see it now. I can see the screen now.
Okay.
Yeah.
Okay. So my name is Karin Habshi and I'm going to teach you engineering mechanics. This course is divided mainly into two parts, statics and dynamics. The statics part will deal with objects at rest or moving at constant velocity, while the dynamics part will consider accelerating bodies. You have two main textbooks, and you can find them easily by downloading them from Google. Okay, so just if you put them, you can download the edition, the 12th edition for statics and dynamics. And I will provide you everything on Blackboard. And already I have posted on Blackboard the different PDFs we will work on, and we will take a look at Blackboard together to see what are the different parts you have in your course material. So as we said, the course is divided into two parts, statics and dynamics. In statics, we will go first over a review of vector algebra. Then we will consider force vectors, particle equilibrium, force moment, and force system resultants. In addition, we will learn how to reduce a distributed force into one force. And you will deal with equilibrium of a rigid body. What is mainly the difference between particle and rigid body? Do you have an idea? Who knows? What is the difference between a particle and a rigid body?
I think a particle is one point in space, and a rigid body is an object.
Yes, so we can say in other words that for a particle, we can neglect the volume, okay?
Oh,
While for a rigid body, it's not the case. And for both, we will consider mass, but in case the dimensions are relatively small or in a certain problems they can be neglected, then we will treat the object as a particle. If not, we will consider it as a rigid body. And finally, in the statics part, you will learn how to determine reactions of supports and how to calculate internal forces of structures. So this is, in summary, the different topics we will consider in statics. Now, considering the dynamics part, we will deal first with kinematics of particle in Cartesian coordinates. And when we say kinematics, it means that we are interested in finding the position, velocity, acceleration of a particle in relation with time or in relation with each other, without considering the forces acting on the particle. Then we will describe projectile motion and dependent motion before moving to kinematics of particle in normal tangential coordinates. So we will see that we have several types of coordinates that can be used to describe motion. When we say Cartesian coordinates, it's the frame you are usually familiar with, IJK. It's a fixed frame, and I express everything with respect to it. While normal tangential frame is a frame that will follow the particle, and we will see together how we work with it. After this, we will study kinetic of particle in Cartesian coordinate. And when we say kinetics, this means that we will consider the relation between forces and acceleration. So before in kinematics, we didn't consider the relation with forces. We just related position, velocity, and acceleration and time. While in kinetics part, we will see how to relate forces to acceleration. And of course, we will do it also in two types of frames, in Cartesian coordinates and normal tangential coordinates. And finally, we will look at the chapter of work and energy, which will relate work of forces to the energy of the particle. So this is in summary our plan for this course. Now, hopefully, after this course, we will be able to draw and use in a proper way the free body diagrams. When we say free body diagram, this means we are representing all forces acting on a body. And the free body diagram is a very important step to start our problem. We will use it in statics and we will use it in dynamics. Second, we will be able to determine forces and couples in equivalent systems. So when we say equivalent systems, this means that they will have the same action, okay? Then we will be able to reduce distributed forces and couple and determine reactions and internal forces for statically determinate structures. And finally, we will learn how to solve kinetics and kinematics problems of particle and system of particles, and to use Newton's law to solve dynamics problems. Now, we will deal mainly with mechanics in this course, which is a part of the physical sciences concerned with the state of rest or motion of bodies that are subjected to the action of forces. Mechanics is very wide, and you have several topics. You have mechanics dealing with rigid bodies, you have mechanics dealing with deformable bodies, and we have fluid mechanics. So in this course, we will deal with the first part, rigid body mechanics, which will consider only non-deformable bodies. So we neglect any deformation. You know that in real case, every body will undergo a certain deformation. But when it is very small deformation on the micro scale, then we can consider that it's a negligible deformation. And we will consider that it is a rigid body. And when we say rigid body, this means that we will not have relative velocity between the particles of the body. While for a deformable body, for any two particles, they can move with respect to each other, which is not our concern in this course. And in rigid body mechanics, we will divide this part into statics and dynamics. And as mentioned previously, statics consider particles or rigid bodies with zero acceleration. And when I say zero acceleration, this means constant velocity vector. So, or it is at rest, or it is moving but with constant velocity vector. And for dynamics, we are dealing with accelerating bodies where sum of forces is equal to mass times acceleration. Please stop me if you have any questions. So as we mentioned, statics is only concerned with objects at rest or moving with constant velocity, and dynamics deals with accelerated motion. So we said that in mechanics of a rigid body, we will consider that we have no deformation. And as I told you, in real life, everybody will undergo certain deformation. But when they are at the micro scale, they can be neglected. Now, the basic concepts we will use in this course are length, time, mass, and force. And you know that length is needed to locate the position of a point in space, and it will describe the size of the physical system. Time is conceived as a succession of events, and it's not important for static problems because, as we said, we don't have variation in time for statics problems, while it's a very important parameter in dynamics. Mass is the property that defines the gravitational attraction between two bodies and is a measure of the resistance of matter to change in velocity. Why we define mass in that way? Because mass is mainly used in the Newton law, sum of forces equal ma. So it represents the capacity of the object in opposing acceleration. So this is how they define it first. Now, considering force, force is the action of one body on another, and it can either happen when there is direct contact or when bodies are at distance. So you know that, for example, contact forces, you have the normal reaction between two objects, or any force applied on an object at a certain point of the object is a direct contact force. While, on the other hand, we can have forces at distance, like the weight, which is the action of the earth on any body, and you can have magnetic forces. So if you have two objects at a certain distance, but there is a magnetic field, so they can attract each other, or we can have repulsion between each other. Now, first we will deal with particles in this course, okay? And then we will deal with rigid bodies. So for a particle, it is defined as a mass which has a negligible volume. Okay, so the size is neglected, but of course we cannot neglect the mass. Now, when a body is treated as a particle, the principles of mechanics reduce to a simplified form, since the geometry of the body will not be concerned in the analysis of the problem. So of course, dealing with equilibrium of a particle will be much easier than studying the equilibrium of a rigid body. And we will see together that the condition of equilibrium of a particle is simply sum of forces equals to 0, while for a rigid body, you have two conditions, sum of forces equals 0 and sum of moments equals to 0. So for a rigid body, it is a combination of a large number of particles. In a rigid body, all particles remain at a fixed distance from one another after applying a law. In general, the assumption of rigid body action is realistic since actual deformation in structures, machines, and mechanics can be neglected. Now, the main laws that we will deal with in this course are Newton's 3 laws of motion. And there are very important laws that we will use in solving our problems. So the first law states that a particle originally at rest or moving in a straight line with constant velocity will remain in the state even if it's not subjected to unbalanced force. Okay? So what do we mean by this? So if you have any system and you draw the free body diagram of this system. What I mean by free body diagram, as I said previously, it will represent all forces acting on this system. If you draw your forces and you do the summation and you get summation of forces acting on it equal to 0, and when I talk about summation of forces, it's a vectorial form. So summation of vectors of forces equals to 0. Then I can say that this object will have or constant velocity or will remain at rest. So it depends on the initial state. If you give it an initial velocity, it will remain with the same velocity for in infinite time, of course, if the forces are not changing, or if it's initially at rest, or you apply a set of forces in a way that sum of forces equals to 0, it will remain at its position. Okay? So this is the first law of Newton, and of course it is concerned with the statics part. While for the second law of Newton, it is given that sum of forces on a body is equal to mass of the body times acceleration of the body. And whenever you see the letters in bold, this means that they are vectors. Okay? So sum of vectors forces equal to mass, which is a scalar, times acceleration, which is a vector. So this law is mainly used in dynamics part to relate forces acting on a body to the acceleration of the body. And finally, the third law, which is very important, is used both in statics and dynamics, and it states that the forces of action and reaction between two particles are equal, opposite, and collinear. So what we mean by this, if you have any two bodies of any size, irrespective of the size, okay, of the bodies, the force of one body on the other, and for example, if I have a small ball and a very large one in contact, okay, if I call the small one A and the bigger one B, and they are in contact, that I can say that the small ball will do a force on the big one, and by action-reaction, the big ball will do on the small one a force that is equal and opposite. Equal in magnitude, opposite in sense, and of course they are collinear. Okay? So if I call, for example, this force, so this is F, this is F of B, F of A on B. So by action-reaction, the force of B on A will be equal and opposite. So this is F of B on A. Okay? Now, a particular application of the principle of action-reaction is the Newton's law of gravitational acceleration. This law will give a relation between for the attraction between two particles. Okay? And it states that if I have any two particles, and they are not, they should not be in contact, that they can be at a certain distance. If the first has a mass m1 and the second has a mass m2, and the distance between their centers, so if I take the center of the first and the center of the second, I call the distance between the centers r, then I can develop a certain relation for the attraction force between these two particles. And this force of attraction at distance is given by G, which is a universal constant of gravitation, times m1 times m2 over r squared. So any two particles will have a certain attraction between each other. And as you can see, the constant G is very small. It's to the order of 10 minus 12. So if the mass of one of the particles is not very high, then this attraction force is negligible. Now, the main application of this formula is what? Do you know what is the main application of the force of gravitation?
In what terms are you saying this, doctor? I mean, we can say, maybe how two planets or two.
Yes. Very
they
good.
can't attract each other, like the sun and Earth,
Exactly.
the moon and Earth.
Yes, exactly. Or يعني when a planet is involved, this formula will become important. And the application that you know very good is what is the action of Earth on any object. What is the force representing the action of Earth on any object? The weight. Okay? The
Ah,
weight represents the attraction between Earth and any object. So if we replace m1 by mass of the Earth, okay, then we will get that F is g times mass of the Earth times m2 over r squared. Okay, and in this case, this represents what? Look, I will write it here. It will be presented here. Look, if I consider as application of this formula the Earth and any particle of mass m, okay, and I want to find the weight. So the weight is the attraction force between them, and it can be calculated as following: g times mass of the Earth times mass of the particle times the distance between the center of the particle and the center of the Earth. So in general, if we consider a particle the surface of the Earth, then the distance between the centers is nearly what? It's equal to the radius r, the radius of the Earth r. Okay? But in reality, in many cases, we have a certain elevation between the particle and the Earth. But in most applications, this elevation is very small. So when the altitude of a particle is much smaller compared to the radius of the Earth, we can consider that the distance separating the centers is equal to the radius of the Earth. And the weight will be given as g times mass of the Earth times m over radius of the Earth square. And as you can see, this term, it will give you what? It will give you the gravitational value of g. You are familiar with g equal to 10 or 9.81. Okay? So G10 or G9.81, which we use for calculation of weight, equals to m times g. This value of 10 or 9.81 is only valid for case of small elevations, because only if the elevation or altitude of the particle from the surface of the Earth is very small, I can neglect it compared with the radius. While if I have a very high altitude, so if I deal with satellites application, then for the altitude or the height separating the Earth from the satellite is very large. And in this case, if I want to calculate the force acting between them, okay, I should consider the distance. So if this distance is high, I cannot neglect it. So in this case, what will become G? G will become the gravitational constant times the mass of the Earth over radius of the Earth plus, so here I should add here plus h, and the whole term will be squared. Okay, so I should add here to the formula plus h, okay, to the formula. So in this case, I will obtain g smaller than 1, because as you can see here, if this will increase, if this term will increase, g will decrease. This is why, if you remember, when we deal with satellite applications, we say that the weight of a satellite can be neglected, because the distance between the center of the Earth and the satellite is very high. Okay, and in this case, this will give you a value of weight nearly equal to 0. So keep in mind that the weight is not a constant, it's a variable, and it's related to the distance between the center of the Earth and the center of the considered particle.
Doctor,
So
you said
value
the,
of g, or acceleration,
yeah, sorry.
sorry,
You
yes,
said the
tell me.
h is the distance between the center of the Earth and the particle.
No, h is the distance between the surface of the Earth and the particle. So
Oh,
the total distance from between the two centers is the radius of the Earth plus h. Okay. Now, if you consider that h is from center to center, then you don't put over radius Earth plus h. You just put over h squared. Okay. So it depends how you define h, because at the end you need to take the whole distance separating the centers. So if this is the Earth and this is the particle, okay, you need to determine the whole distance from the center to the center. Okay, so if I consider that this distance from here to here is h, then the total distance will be h plus radius of the Earth. Okay?
yeah.
If not, if you want to name the whole distance h, you can. And it's not a problem. Just you should know that you should consider the total distance between the centers. Okay?
Yeah. Yes, thank you.
Okay. Now, considering the system of units, we have two main systems that you will work with in this course. We have the SI units and we have the English units. You are familiar with SI units, the International System of Units. So mainly for length, we have meter, for mass, kilogram, and for time, seconds. While for the English units, for length, it's foot, for mass, it's slug, and for time, it's second. So just you should know that if I deal with English system, then I will use feet, slug, and LB for forces, while for international system for forces, it's Newton. Okay, and the value of G will not be the same for both, because in SI units, G is meter per second square, while in English units, G will be in feet per second square. So you should know just the value of G in both systems. So in for G in SI, it's 9.81, and I repeat, this is for small elevations of the particle, while in English system, G is 32.2. Okay, so just this is what you should know about units, and you can convert easily from one system to the other, because here, for example, W equal mg. If you are working in English system, then the weight is in pounds, lb, the mass is in slug, and g is in feet per second square, and it's equal to 32 or 32.2. Now, to go from one system of units to the other, these are the conversion factors. So 1 feet is nearly 0.3048 meters. 1 lb represents 4.448 Newton, and 1 slug is 14.59 kilograms. Now, we will deal mainly with scalars and vectors in this course, and it's very important to know the difference between them. So a scalar is a quantity that possesses magnitude only. So if I just give you the magnitude, it's completely defined. So which is the case of mass, area, volume. So if I tell you an object is of mass 3 kilograms, then it's enough for you to know everything about the mass. While a vector is a quantity that possesses magnitude and direction. Okay, and to define it, in general we have 4 properties: point of application, magnitude, direction, and sense. Okay? And in order to represent a vector, we can have several ways. We are familiar with this notation, where you have the letter with an arrow above it. You can see it as bold letter, as we have seen here in this presentations, or you can have it underlined. So if you see any of these three notations, all represent a vector. Now, the magnitude of a vector is we can represent it like this. Now, sometimes you can see this. This is also for the magnitude, okay? And sometimes for magnitude, we just put F, like this. We just put F equals. So this is also a representation of magnitude. So as we have seen, the vector is defined by the following properties. So first, you have the point of application. So at which point the vector is acting. Now, in case the point of application is not of interest, we call it a free vector. So wherever I put it, it will have the same effect. We will see together that the moment vector is a free vector, while the force vector, no. For the force vector, it's important to know its point of application. Okay? So, first, we have the point of application. Second, we have the magnitude to be able to know what is, if you want to measure, if you want to draw a vector, I should take a scale and I should know its magnitude. Draw it. Of course, I need to know the direction, which can be defined in several ways. I can define it as an angle. So I give an angle with a known reference. So here, for example, if I consider the horizontal as my reference, okay, then the angle between the horizontal and the vector will give me the direction of my vector. I can give it in components. So instead of giving angle, I can say, I can divide it into components. So by knowing the components of the vector, then you can automatically deduce the direction, okay? Because we will see together that if you know the magnitudes, for example, in x and y, how you can find the angle, what should we do then? If you know px and py, how you calculate the angle here?
We use tangent. Yes.
Yes, very good. So we do tangent minus 1. So tangent of the angle is this length, which is py over px. Okay? Now, for the sense, it's indicated by the arrow. It can be up or down, so it depends on the vector. So, for example, here, an example of vector is displacement of a beam. So, if you have a beam or a column and it undergoes a certain deformation, the deformation can be considered as a vector which has a magnitude, a direction, and a sense. And of course, the force is a vector. So, if I consider the weight, the magnitude of the weight is mg, the direction is vertical, and the sense is down. Now, we have several operations that can be performed on vectors, and it's very important to know these operations because we will work a lot with vectors in this course. So first, I can multiply and divide a vector by a scalar. So, for example, here, if I have vector A, if I multiply it by -1, I will get the opposite vector. If I multiply it by 2, I will have a vector that is of same direction and sense, but has a magnitude that is doubled, okay? And if I multiply it by a negative scalar, then it will be in opposite direction, and the magnitude, so if I multiply by -1.5a, I'll have a vector of opposite direction, but the magnitude is just multiplied by 1.5. Now, I can never divide a vector by a vector. We don't have division of a vector by a vector. I have division of a vector by a number, so a over 2. but I cannot put A vector over B vector. It doesn't have any meaning. So never we divide vectors. Now, also we don't have multiplication of vector by a vector. We have two other applications, which are cross product and vectorial product, and we will define them now. So if a vector f is multiplied by a positive scalar a, the new vector will have a magnitude that is equal to a times f, and the same direction and sense as f. While if f is multiplied by a negative scalar, the sense will become opposite. So we also multiply and divide a vector by a scalar, not by a vector. Now, what are the operations that we can do on vectors? The first operation is addition. I can add two vectors. And to perform the addition of two vectors, I have several ways. I have analytical way and I have geometrical way. What do I mean by this? First, for the geometrical way, as the name indicates, I am using geometry to do the addition. So if you have two vectors A and B, and they don't have to have the same point of application, but if I want to add them, I will start from one point. I will draw a vector that is parallel to A. I will draw a second vector that is parallel to B. Okay? And now, if I complete my parallelogram, as you can see here, the diagonal, which starts from the point which is common between A and B, I get the resultant, which is A plus B. So this is called the parallelogram law, which can give me by geometrical method the resultant. Okay? So we will learn together how to calculate the magnitude and direction of the resultant using the parallelogram law. Another method, geometrical method also, is called the triangle construction. So what I do is, I have two vectors A and B. Instead of, so if you want to understand more, I will show it on the same slide here. So for the parallelogram law, you start from common point, you draw vector A, and from the same point you draw vector B. And you, from this point, you draw the diagonal, you get the resultant. The triangular construction is the following. I draw a first vector, and now from the end of A, I draw a vector parallel to B, like this. Okay? Then, if I join, we say we join tail to head. So if I join the first point to the end point, I get the result. Okay? So, and in general, we use the triangular method because we have the laws of cosine and sine, which can be applied to a triangle, and that will allow us to calculate all our unknowns, as you will see in details together. So this is the triangular construction, and as you can see, you have several ways to do it. So if you start by vector A, then by vector B, you get A plus B. You can also start by B, then by A. And of course, it's the same result, because A plus B is equal to B plus A. So as you can see, you'll obtain the same vector. So in triangular construction, what we do is we have head to tail joining. Now, operations on vectors. We will continue with the operations. We said that the first operation is addition. The second operation is subtraction. So I can do A minus B, and it's equivalent to A plus minus B. So it's very simple. All I have to do is to take the vector that is opposing B, minus B, and then I perform the addition. If I want to use geometric way, I can use the parallelogram law or the triangular construction. Both will give me the resultant vector A minus B. Now, if I have more than two forces to be added and I want to use the geometrical method, I should have successive implementation of the parallelogram law to obtain the resultant force. So as an example here, if I want to do F1 plus F2 plus F3, I can start first by adding vectors F2 and F3. I get the resultant here, the first vector in red. Then F2 plus F3, I add it to F1 to get the final resultant, which is F1 plus F2 plus F3. But as you can see, if I have a number of vectors, the geometrical way becomes non-practical. Okay? This is why we will see a more practical way to calculate, to find resultant of forces, which is the analytical method. So for the analytical method, what we will do, we will decompose any force vector into components. And then, if you want to perform the addition, all we have to do is to add components. So, for example here, if I consider any frame, and it should not be Cartesian by force. So when I take Cartesian orthogonal frame, this means that the axes are perpendicular. But I can take any directions for my axis. They can be perpendicular, but they can be with a random angle between them. Okay? So here, if I take any two axes, A and B, I can decompose R into two components, one along A axis, one along B axis. How to do it? All I have to do is to get the component along A axis, I take the parallel to B axis. Okay, it will have a certain intersection with A. So as you can see here, this is the magnitude of along A. You can have the vector not starting from origin. If the vector is like this, for example, like this, how can I find its projection on A? All I have to do, so I start from the tail, which is the start point of the vector. I take a parallel to B. Okay, it will intersect A axis at a first point. Then I take the head of the vector, and also I do a parallel to B. It will cut the axis at another point. And then by joining the 2 points, I get the projection on A axis. Okay? The same to get the projection on B. Now I do parallels to A axis. So for example, for the same vector, I take first parallel from the tail point, the first point, to A. And then I take another parallel line to A. Okay. So here we cannot complete it because of the space. Okay. So if you join the 2 points, you can see it here for this force. If I join the 2 points, I get the projection on B. Okay. So by dividing into components a force, to do force addition, we will see that it's enough to add the components along B and add the components along A. So we can have then the components of the resultant. Any question on this? Please, if you don't understand anything, just stop me and ask. Okay? So now, we will see together some laws that can be used for geometrical calculation of a force magnitude and a force direction. Okay? So if I have a triangle and I know magnitudes of its of lengths of edges. So for example, here if I know A, B, and C, and I know angles for the triangle, we have a law called Sine law that permit to relate the magnitude of edges and the angles. And this law states that if I take any edge, A for example, okay, if I do A over sine of the angle that is opposite to A, which is here small a, it will be equal to B over sine of the opposing angle, which is B, equals to C over the opposing sine angle, which is sine C. So I can write that A over sine A equals B over sine B equals to C over sine C. Okay? So if I know, for example, if I know A and the angle small a, and I just know B only, I can deduce what is the angle small b. Okay? So if it's enough for me to know 3 parameters to determine the first one. Or for example, if I know the angle small c, I can calculate using this relation the magnitude c. So the sine law is very important to determine magnitude of forces and their direction. And we will do a lot of applications on it. Another application that is very important is the law of cosines. So if I have a triangle and I want to, for example, calculate the magnitude C, I should know, to use the cosine law, I should know the following. I should know the magnitude A, I should know the magnitude B, and I should know the angle between A and B. Then I can write that the magnitude of C is radical A squared plus B squared minus 2AB cosine C. So this is the cosine law. And in particular, if C is equal to 90 degrees, then you will use the familiar Pythagorean theorem, which is C equal radical A squared plus B squared, because cosine C will be in this case 0 when C equals to 90 degrees. Okay, so this is our session for today. Just before closing, I just want to tell you how the material is divided in Blackboard. So do you see now the Blackboard screen?
Yeah.
Yes.
Okay. So first, in the course syllabus, you can find all details about the syllabus of the course. It will tell you about the main material we will take, which was introduced in this session. Now, in general, we do 2 exams and 1 final, okay, with the percentages are all presented in the course syllabus. Now we will agree together on dates for the exams. I will try to give you dates much earlier so that you can organize your time. For course material, here you have the all slides that we will do together. So already everything is posted for you for the different chapters we will go over. So today we started with introduction. So when you download it, you can have the slides we worked on today. Review problems is a section where I selected some important problems on all chapters for you to practice. For the introduction, we don't have problems. We will start with review problems in next chapter, which is chapters on vectors and forces. And for each chapter also, you have sometimes a summary sheet, which will tell you what are the most important ideas in each chapter. And after, I will post for you previews so you can practice for the exam. Okay, so these are mainly the main components on Blackboard. And if we add anything, I will update you. Okay, thank you. So see you next time.
Thank you, doctor. Have a nice day.
Thank you.
Doctor.
Thank you, doctor.
Welcome. Bye.
Thank you, doctor.
Bye. Bye.